Hello everyone, welcome to video 5 part 4. In this video we continue to look at the calibration of the Danube watershed. If you recall, we took a small watershed in the Danube Basin, and the details of this project, which comes from our European and Black Sea project, can be found in these papers. Now, to update you on what we did before, first we produced an initial simulation, and we got some values for Gneiss cliff that there were quite a few negative numbers in our initial model. Then we fitted P-labs and T-labs, and here the model improved quite a bit from a negative Gneiss cliff to a positive Gneiss cliff. And then we fixed the T-labs and P-labs parameters to the best values that we obtained. In the next step, we fitted the snow parameters, the 5 snow parameters, and the Gneiss cliff of the overall model improved a little bit more, but not too much. And we discussed why that was. That was because we had a lot of climate stations on top of the mountain, so there was nothing we could gain more from our climate data. Then we took some parameters for the first two outlets, outlet number 6 and outlet number 8. We parameterized these two outlets, and then we made an iteration. And the overall objective function improved again to 0.33. And if you look at the Gneiss cliff of the different outlets, they all showed quite a bit of improvement, but still there are many of them are small Gneiss cliff values. Now remember that we only parameterized the first two outlets, but then our objective function contains all 11 outlets. That's just how we did that. Now, if you look at, there are several things that I'm going to show you, but first I would like to show you some graphs that I've already done. Once we do a run, it is very easy to change the objective function and look at the results for the new objective function. Now, our iteration number 1 was based on a Gneiss cliff objective function, and this is what we got for, let's say, outlet number 8. And then I changed the objective function to BR squared, and this is what I get for BR squared. So the red line is my best simulation, the blue line is observation, and the green band is my 95% PPU. Now, if you notice, there is quite a bit of difference in the best parameter or the best simulation that I obtained between BR squared and Gneiss cliff. Here you see the red line. The base is very much underestimated everywhere, right? And you see the peaks are overestimated everywhere. But if you look at the Gneiss cliff, it's sort of a smooth curve that runs through the middle of my observation. So different objective functions really give you different best parameters that are quite different. And now, if I use any of these, Gneiss cliff or BR squared, to go further to do the second iteration, I have to follow completely different strategies for getting, to get my new parameters and run another iteration. The new parameters are quite different. Here I have to try and sort of fix the base flow, make the base flow higher, make the peaks lower, and here I have to sort of do the opposite. Of course, base flow here is not so bad, but the peaks are very much underestimated. So the strategy of going forward, if I use Gneiss cliff or BR squared, will be quite different. Now let's look at what happens to the summary statistics if I do Gneiss cliff versus BR squared. Here you see that the best simulation number is different. Of course, we saw they were quite different best simulations. And the best goal, of course, this one reflects Nye-Sutcliffe and this reflects BR². But if you look at, when we use Nye-Sutcliffe, if you look at the Nye-Sutcliffe values, they are much higher than if I use BR², right? In BR², I have quite a few, I have 4 negative Nye-Sutcliffe. So when I use Nye-Sutcliffe, the best values are Nye-Sutcliffe. If I use BR², BR² gets much higher values compared to BR² when I use Nye-Sutcliffe. So objective function makes a lot of difference on your everything, on the statistics, on the parameters, on the sensitivity analysis, and so on. But notice that in these two cases, P factor and R factor are the same, because P factor and R factor are based on the whole entire 800 simulations. So this would be quite different if I use behavioral objective function, which I will show in the next videos. But in this video, because P factor and R factor in a single objective function are based on the entire 800 simulations, so they are the same. But the best simulations are quite different. So visually, you can see how different they are. This is BR², and that's Nye-Sutcliffe for outlet 6, and BR² and Nye-Sutcliffe for outlet 8. So if I use BR² as my objective function, my best simulation is very different than if I use Nye-Sutcliffe, right? And you can see the differences. And then if I go further and I do sensitivity analysis, so if I do Nye-Sutcliffe sensitivity analysis, here I should be looking, we should be looking at the p-value. P-value should be small, about this size, to be meaningful. The sensitivity of a parameter to be meaningful. So I would say the first five are meaningful. They have meaningful sensitivities. And so for Nye-Sutcliffe, and the same with BR², the first 5 have meaningful sensitivities. So here you have groundwater delay for subbasin number 8 and above number 8. So this is the most sensitive, so they both agree here. But here the next one is groundwater recharge, deep aquifer recharge. And here I have deep aquifer recharge as a lower level sensitivity. And then here I have CN², which is, CN2, which is the third, ranks 3 because of the t-value. And here CN2 ranks second. So they are more or less the same, a slight different in the ranking, but they all agree quite well. And that shows the sensitivity analysis that we use is quite meaningful, is not absurd. It is meaningful, the values that we get. But from iteration to iteration, of course, the ranking changes, right? You don't expect it to be exactly the same because of issues that I discussed before. They are going to be different from iteration to iteration and from objective function to objective function, but the difference is not huge, right? The difference you can live with. Now let's look at the parameters, the most important thing when you use different objective functions. So the fitted values, if I use Nye-Sutcliffe versus BR², you see they are very different. They can be really substantially, significantly different from each other. And this is where the problem lies in the choice of objective function, is that if you use one objective function and you calibrate your model, you end up with a different set of parameters. The best parameters and also parameter ranges will be quite different than if you use another objective function. So which one should I believe? And if I use this parameter set to calculate, for example, the water resources of my watershed, and if I use this set of parameters to calculate the same water resources, I'm going to end up with significantly different numbers. So which number should I believe? So this is one problem really with the single valued objective function, and that's why I discussed the conditionality and so on. So I have spoken a lot about this, that using different objective function. That's why we went to behavioral objective function and multi-objective function, because these parameter sets now are conditioned on the choice of my objective function. Well, they shouldn't be, right? I should have unconditional parameter set. So regardless of what objective function I use, I should end up with the same value of water resources for my watershed. So that's why I need unconditional parameter sets, and to get unconditional parameter sets, you have to use multi-objective simulation or calibration. That's when you include all the objective functions. So to get from conditional to unconditional of anything, you need to integrate over all the variabilities. So in this case, it would be my objective function. So I have to integrate over all or a representative set of objective functions. Now I discuss about this. We have done some of these analyses in these two papers that you see here. And I really encourage all the scientists, analysts, researchers who are working as the master or PhD degrees to have a deeper look at this, of the issues, of what you're doing, really. Every step of the way, you can question if what you are doing is right, or could you be doing something else, or what is the meaning of it? And we need quite a bit of new ideas here. As you can see, calibration of distributed watershed is really quite a challenging issue. And at the end, you know, if you try different things, you keep asking yourself, so what does that mean? What does that mean? Does that mean anything? So I hope you keep asking yourself that question, and you try to further our knowledge a little bit more in this calibration exercise. All right, so let me just show you how we do this in SWATCUP. If you remember, that's where we were last time. We had parameterized the first two outlets. We had 22 parameters, and we did 800 simulations. And our objective function is number 5, which is nice Sutcliffe. And then we are including all 11 outlets in the objective function. I mean, we could have included just the first two, but that's just what we are doing. In reality, you should have parameterized all 11 outlets. So we finished the iteration, and then I did the post-processing here. Let me just do this quickly. All right, so this is done. And then we can just look at the output, and these are the things that I've already shown you. This is number 6 outlet, number 8 outlet, and then the rest, even though we didn't parameterize them, but because they are on the same river network, parameterizing the first two affects also the ones downstream. Further down, these are not on the same river, so the parameterization of the first two did not affect these other outlets. And then we had the summary stat, which I showed you before in the PowerPoint. Now, to get the result, if I want to change objective function, it is really quite easy. So let me close this. All I have to do is I go to, because all the simulations are done, so just here I have to change this to whatever I want. Say try number 6, which is BR squared. So I save this, and then I simply run the post-processing, and that gives me the results for BR2 squared objective function. Okay, and then I can visualize the results for BR squared, and these are the things that again I have shown you before in the PowerPoint. So you see with BR squared we have in many outlets quite a bit of base flow problem, and the summary is set and so on, and I can do the sensitivity analysis for this case and global sensitivity, and also for the Nye-Sutcliffe and so on. And here is my sensitivity information, which again I have shown you before. So it's very easy to change the objective function and see the results. You could do this, you could choose any of these 11 functions as your objective function and see the difference, which I have shown you that the difference is really huge. Now the next thing we want to do is to run a second iteration. We did iteration number 1, and let me go back to Nye-Sutcliffe. So from here I could go on either using Nye-Sutcliffe or using BR squared. As I said, our strategy would change a little bit, but to stay with the Nye-Sutcliffe, let me just change this back to number 5, save this and close these. We don't write on these two files, so we can keep them open, but the other ones, the program needs to write them, so we need to close those. So I save this change, and then I just run the post-processing again to get my results for Nye-Sutcliffe. I mean, each time I could have saved the iteration under iteration 1 Nye-Sutcliffe, iteration 1 BR squared, and so on. And now to do the second iteration, what I have to do is get the new parameters here. So these are the new parameters which have been sort of simulated. Parameter ranges have been simulated, and I can simply copy this here, copy and paste it in my parameter information file here. And so here we have number 6. So these are the new ranges. These new ranges are centered on the best simulation of the previous iteration. So usually you have to go through this to make sure that sometimes hydraulic conductivity can be negative, you know, because these are simulated values, or groundwater parameters could be negative. So you need to edit, you need to look at these parameters, right? And what I do usually, I try to, because in every iteration the range decreases. So therefore your P factor and R factor decrease. So what I do usually with the new parameters is I try to expand the range of the parameters here a little bit. So if it's negative, I go to the next, sort of round these to the rounded value. So I go from minus 0.2 to 0.2. So expand the range a little bit so that I don't miss any good simulations or parameter sets in between. And I do this with all of the parameters. I just expand it. So this is 0.23. I go, for example, to 0.2. So decrease the lower one and increase the higher one. So I take this to 0.8. And I do this to all of these parameters. Okay, so I did that for all the parameters, just expanded this range a little bit, and now I can do a second iteration. And so I just save all and close all, and then do a second round of iteration. So iteration number 2 was finished, and here I have the summary of all the runs. We made a small improvement between iteration number 1 and iteration number 2. And as you can see, P factor is smaller and R factor is also smaller. Every iteration, the range of parameters usually get smaller, even though we expanded it a little bit, but still the range was smaller. And as the range of parameter gets smaller, R factor gets smaller, and consequently P factor gets smaller. So by going from iteration number 1 to iteration number 2, we gained very little in terms of overall objective function. Our NISOT cliff for iteration for the best parameter, as you can see here, has improved. But nevertheless, we lost quite a bit of P factor. That means the percentage of observed data within the 95 ppU. So what I would do at this point is I'm not going to iterate anymore, right? So you can see that the iteration did not bring us very much. So for this project, I am just going to accept the parameters that I obtained in iteration number 1. Because iteration number 2, I mean, the most important thing is the P factor and R factor, not the one simulation specified by this value of NISOT cliff, the so-called best simulation. So I would stay with iteration number 1, and that is my solution to the calibration problem. But the results, I would say, are not so bad. So I would not go any further because this is what I have. Now, Danube is a very busy watershed, and as we saw at the beginning, there are a lot of urban areas, a lot of agricultural areas, so there is a lot of water management. And so you should not expect to, if I can go back to one of the our simulations here. So for example, here you can see I don't expect to meet, should not expect to meet all the peaks and all the base flows and the exact dynamic of the flow, because I am not providing the model with all the necessary information, with everything that is going on in the watershed in terms of water withdrawal and input into the system, which there is a lot. We know there is a lot of management. So I should not expect to have a perfect fit. So what I have here, and this is from iteration number 1, I think it is the best that I can achieve unless I provide more information to the model. So for this exercise, I am just going to stop here and not go any further. And these are the results that I have, which reflect the information that I have put into the model. Now remember that the information that I use for this comes from the much larger European project. So to go from a very large project to a small watershed within that project, what I would need is more accurate data. And you see, all of these things are showing in my result. I would need to have more accurate soil, more accurate land use, more accurate management practices, and so on, when I go from a large watershed to a smaller watershed. So this is what is happening, and that is very well reflected in my calibration. And so that would be where I stop this project. Now, in the next video, I will show you what happens if I use different types of objective functions. So if we use, if I use, for example, a behavioral objective function or multi-objective function, what would happen, and will I see any differences, or would I get the same sort of results? Now, what I'm going to show you, last time I said I'm going to say something about the base flow. So maybe this would be a good time to tell you a little bit about the base flow, and that if you want to account for a process, you really need to know the science behind it and to know where you can influence that output that you would like to see. So let's go to this base flow. So now the question becomes, how do we calibrate for base flow? Here is a conceptual model of SWAT water balance. Everything begins with precipitation. Precipitation divides into runoff and infiltration. Water that infiltrates becomes, first of all, water storage of the soil. Then part of that becomes return flow. It goes back to the river, and it's mostly responsible for the base flow. Then you have aquifer recharge. And then you have revap, which will bring water from the aquifer back into the root zone. Then you have evapotranspiration. So if you want to increase base flow, what you want to do is to increase return flow. To increase return flow, you could increase infiltration. You could decrease water storage capacity of the soil so that more water can escape the soil. You could decrease aquifer recharge, and you could increase revap. Finally, you could decrease evapotranspiration. Now, some of these processes are parameterized. There are parameters to decrease this, and there is parameter to decrease soil water storage capacity. There is parameter to increase revap. We don't have too much control on evapotranspiration because this is governed by the atmospheric demand and partly by soil hydraulic conductivity. But SWAT doesn't go to that detail for soil hydraulic conductivity. So there are a few parameters that we can adjust to increase the return flow into the river. But often these parameters are not enough. And there are other processes that are important, such as water that comes from the water treatment plants, water that comes from the springs, if you are in a mountainous region especially, and water that comes from the complicated underground flow that can put a lot of water into our system. Now, we have a watershed in the middle of Danube. There are mountains. Clearly, there is water coming through underground flows into the Danube River from outside of our watershed. So, and other sources. All of these put together, they give us the point sources in SWAT. So you can account for all of these at the same time with point sources. Now, point sources are not parameterized. There are not parameters that you can add or you can change. So what you have to do is to just put direct water into the system or take it out of the system if you want to increase or decrease base flow. So these are the things you can do. Now there is another thing that you can deduce from this schematic picture, and that is runoff is only one component that directly influences river discharge. So watersheds that are runoff dominated are easy to calibrate in SWAT. However, watersheds that are infiltration dominated are difficult or more difficult to calibrate in SWAT simply because of the many processes that are involved. So you should keep that in mind. If your watershed, sometimes it's easy to calibrate, sometimes it's very difficult to calibrate. And for the water that infiltrates, we really don't know any of these. We don't know any of these. So we don't have too much confidence on how much weight to put on which factor. There are only very few watersheds that have such information, but mostly we don't have that information. So keep that in mind that if your watershed is infiltration dominated, you're going to have a harder time calibrating that model.